This video discusses a high-speed, learning robotic table tennis system and showcases many of its key features. Robotic table tennis is a challenging high-speed task. The ball moves very quickly, so the system must be able to sense, react, and adapt in real time. First, we talk about the main components of the system. The system uses a 6 degree of freedom ABB arm controlled at 248 Hz. These industrial robots can execute actions with high reliability and accuracy, while still imparting significant force when needed to return the ball. The arm is mounted on a two-dimensional Festo gantry, controlled at 125 Hz, that can move up to 2 meters a second along both axes. The gantry allows the arm to cover a large play area, similar to professional table tennis players. To enable automated experiments, an off-the-shelf ball thrower was heavily modified to be controlled programmatically over USB. When the thrower runs out of balls, it triggers an automated refill. First, a ceiling-mounted fan clears any balls stuck on the table. Then, blower fans on the floor direct the balls around the table. Eventually the balls reach a ramp, which directs them to a tube, and up to another ramp that deposits them back into the thrower. In this way, the system can work without human intervention for long periods of time. To detect balls, the system uses two synchronized Shyamir cameras that run at 125 frames per second. A temporal convolutional network detects the balls in each frame, and then triangulates the 3D location for high accuracy, low latency ball positions. Policies are trained in simulation using an evolutionary strategies approach called black box gradient sensing. These policies can be transferred to real robots with high zero-shot performance and can also be fine-tuned on a real robot with the same method. The system runs commands through a safety simulator to protect itself and the environment. This policy might have hit part of the gantry if the safety simulator hadn't redirected it. Here we present several experimental results from the accompanying paper. In this experiment, we varied the amount of latency that policies were trained with in simulation. Training using the measured real system latency results in strong zero-shot transfer performance. Policies trained with no latency swing at the ball too early. Training with 150% of measured latency has the opposite effect. The robot swings too late. In this experiment, we took a strong zero-shot policy and applied additional noise to the ball coordinates. A small amount of uniform noise still allows the policy to perform well, with occasional mistakes. Larger amounts of noise, especially biased noise, greatly hinder performance. While most policies control the robot in joint space, an alternative is to control the end effector directly in task space. Next, we show the same policy in 3 different settings. First, with a different default pose. Second, with 2 of the joints frozen and a different default pose. Last, we show the same policy on a different model arm. Thank you for watching. For more information, please see our paper.